Yeah.
So
So
let's
let's
start
start
our
our
session
session
6
6
on
on
the
surface
phase transformation
transformation
and
and
materials,
materials,
right?
right?
So
Previously, we had
previously we
discussed
had discussed
lots about
lots about
nucleation,
nucleation,
interfaces, and also
interfaces, and
bits
also
and pieces
bits and pieces
about growth,
about growth,
kinetics.
kinetics.
So in this session, we
So
will
in this
be
session, we will be
mostly
mostly
concentrating on the
concentrating
alloy
on the
solidification
alloy
and
solidification
also the
and also
solidification
the
in
solidification
ingots.
in ingots.
So
So
let's start.
let's start.
So before going
So
into that,
before going into that,
uh,
uh,
let's suppose if
let's
you're talking
suppose
about
if you're talking about
two solids
two
or
solids
any
or
transformation
any transformation
for our sake,
for our sake,
you know,
you know,
whether it is
whether it
liquid liquid,
is liquid, liquid,
whether let's say one
whether let's
we are
say
taking
one
one is
we are
here is
taking one is here is
liquid to solid
liquid to
transformation,
solid transformation,
which is
which
solidification.
is solidification.
Right, there is one type of
Right, there is one
transformation.
type of
Now,
transformation.
in this
Now, in
transformation,
this
what we are going to
transformation,
do,
what we are going to do,
we are going
we
to
are going to
during alloy
during
any
any
solidification, either we take
solidification,
alloy
either we
or
take
any
alloy or
pure
any
metal
pure
solidification.
metal solidification.
So we have
So
discussed the
we have discussed
pure
the
metal
pure
solidification,
metal
like how
solidification,
it
like
grows,
how it
like we
grows,
have
like we
planar
have
interface
planar
growing,
interface
and also
growing,
we had
and also we had
thermal dendrites,
thermal dendrites,
depending upon how
depending upon how
our thermal
our
gradient is
thermal
in liquid
gradient
and
is in
solid.
liquid and solid.
So in this session,
So
we
in
will
this
be
session, we will be
concentrating on the
concentrating
alloy
on the
solidification,
alloy
which means we are
solidification,
not
which means we are
talking
not
about any
talking
pure metal
about
now.
any pure metal
Okay,
now. Okay.
so then
So then
in alloy
in alloy
solidification, let's say
solidification, let's
we
say
have
we have
an isomorphous
an isomorphous
phase diagram,
phase diagram,
or let's say we
or
have
let's say we have
elliptic phase diagram.
elliptic phase diagram. Okay.
So
So
let's say this is my
let's say this is my
elliptic phase diagram.
elliptic phase diagram.
Okay,
Okay.
so this is my
So this
A
is my
atoms, and
A
these are
atoms
B
and these
atoms,
are
and
B
we have
atoms,
alpha
and I have
phase,
alpha
we have
phase,
beta
I
phase,
have beta
we have
phase,
liquid.
and I have
This will
liquid.
be my alpha
This will
plus
be my alpha plus
liquid. This will
liquid.
be my beta
This will
plus
be my
liquid,
beta
and
plus
here I have
liquid, and here
alpha
I have
plus beta.
alpha plus
So
beta.
these are my
So these are
phases.
my
One,
phases.
two,
One,
three.
two,
This is
three.
my three
This is
phases.
my three phases.
So
So
and this is also a
and this is
phase,
also a
but
phase, but
this and
these
yeah,
and yeah,
there is a doubt.
there is a doubt.
What do you call this
What do
alpha
you
plus
call
beta?
this alpha plus beta?
It's called as
It's
a
called as
heterogeneous
a
phase because
heterogeneous
we
phase
have
because we have
two phases.
two phases,
Heterogeneous phase,
heterogeneous
but
phase,
still it is
but
called as a
still it is
phase,
called as
right?
a
Then
phase, right?
what are
Then
alpha and
what
beta?
are alpha and beta?
They are micro
They are micro
constants.
constants,
Constituents.
constituents.
So that's
So
how we
that's
call
how
them
we call them
Browns-Lamb when
Browns
there are
them
two or
when there
more
are two or
phases in a
more
single
phases
phase.
in a
We
single
call
phase.
that
We
whole
call
phase
that
as a
whole phase
global phase
as
as
a
the same
global phase
as a phase,
as a
not a single
phase,
phase but a
not a single
heterogeneous
phase but a
phase.
heterogeneous
And my
phase.
alpha
And
and
my
beta
alpha
are
and
two
beta
different
are
phases in
two
it,
different phases in
which we
it,
called as
which we
micro
called as
constants.
micro
Okay.
constants. Okay.
Now
Now
that is about
that is
the
about the
solidification. Now
solidification.
moving on
Now
to
moving on to
yeah.
yeah.
After that,
After that,
let's talk about the
let's
liquid
talk about
solid
the liquid
transformation,
solid
and
transformation,
also
and
think
also
about our
think about our
more
more
like what do we
like
call?
what do we call
Hmm.
mm,
When we are talking about
when
liquid
we're
solids,
talking about liquid
we're
solids,
more
or yeah,
talking
we're
about
more
the
talking
how
about the
the solidification
the
is taking
solidification
place
is
in
taking place
analog,
in an
right?
alloy, right?
Suppose if I have
Suppose if I
just
have
I will
just
take the
I
search
will take the
example
search
to make our life
example to
simpler.
make our life
So
simpler.
let's say this is
So
my
let's say
rod.
this is my rod.
First, it is my pool,
First, it is
okay,
my pool,
and
okay, and
this is my
this is
melt
my melt
in a mold,
in a mold,
right? So let's say
right? So let's say
my melt
my
is in a
melt
mold.
is in a mold.
Now what I'm trying to
Now,
do
what
is
I'm trying to do is
this is now in
this is
furnace.
now in
Now what I'm
furnace.
trying to
Now,
do,
what
I'm
I'm trying
trying
to do
to
is
take it
I'm
out.
trying to take
Let's
it
say
out. Let's say
it was in
it was
furnace
in furnace
at time t is
at
equal to
time t
0.
is equal to
Now what
0.
I'm trying to
Now,
do
what
is
I'm trying
this
to do
is
is this
furnace,
is
okay,
furnace, okay,
which is
which
keeping
is
my
keeping
melt
my melt
in a liquid form.
in a liquid form.
Now at time
Now, at
t is
time
greater than
t
0,
is greater than 0,
I mean after
I
time
mean,
t,
after time
let's say
t,
this is my
let's say this is
furnace.
my furnace.
What I'm trying to do,
What
I'm
I'm trying to
trying
do,
to
I'm
take out the
trying to
mold
take out the mold
slowly.
slowly.
This is my melt,
This is my melt,
this is my mold,
this is my mold,
and this is my
and this
furnace.
is my furnace.
Okay, I'm trying to take
Okay,
out the
I'm
mold.
trying to take
Now
out the
what
mold.
happens?
Now, what
These
happens?
parts will cool
These
down,
parts will cool
right?
down,
Up
right?
to this one.
Up to this one.
Up to this one,
Up to this one,
they will try to cool
they
down,
will try to cool down,
Right, so they are
Right,
trying to
so they are
so
trying to
they will cool
so
down.
they
So
will cool
because
down.
of
So
this
because of
cooling
this
phenomena,
cooling
we will
phenomena,
have
we
a
will have
solidification.
a
Now,
solidification. Now,
what about
what about
what are we talking
what
about?
are we talking about? Like
How it happens,
how
right?
it
So
happens, right? So
now this part
now this part
will turn out to be
will turn
solid.
out to be
So
solid. So
let's say
let's say the
let's
half
say the
of the
one
let's
by
say the one by
third of the part
third of the
has
part
turned
has
into
turned
solid,
into solid,
and this is still
and this
our
is still
liquid
our
melt,
liquid melt.
right?
Right
Now,
now,
when I try to
when
take
I
out
try to take out
this whole
this
mold,
whole
so
mold,
this
so
front
this front
will travel
will
or will
travel
move
or
at
will
a
move
certain speed.
at a certain
Now,
speed.
if you want to
Now,
know
if you want
how
to know
it is
how
moving,
it is
and for
moving,
example,
and for
if
example,
I'm
if I'm
if I totally
if I
take it out
totally take it
and
out
put it in a
and
system
put it in a
where it is
system
covered,
where it
but
is
what I'm
covered,
trying to
but
do
what
is
I'm trying to
I'm
do
trying
is
to
I'm
extract the
trying to
heat
extract
from
the
this
heat
side.
from this side.
Then how this
Then how
front will
this
go
front will go
again.
again.
So to know that,
So to know that,
let's say,
let's say,
yeah.
yeah.
So to know
So
that,
to
let's
know
say
that, let's
I
say
draw
I
a
draw
phase
a
diagram.
phase diagram.
Let's say I'm only
Say I'm
concentrated
only
I'm
concentrated on
at
and
only this
at
region.
only this
I'm not
region.
worried about
I'm not worried
this
about
part. Okay.
this part. Okay.
Now
Now,
the phase diagram
the
still
phase
continues, but
diagram still continues,
not
but
worried
I'm
about
not worried about
that part,
that
right?
part,
So
right?
let's
So
say my
let's
liquid
say my liquid
is at this
is at
composition,
this composition,
which is at
which is at
x naught
X naught
composition. Now to make
composition.
our
Now,
life
to make
simpler,
our life
we
simpler,
relate
we
our
relate our
mole fraction
mole
or
fraction
the
or
fraction of
the fraction of
solute or weight
solute
fraction
or
of
weight
solute.
fraction of solute.
Let's say,
Let's say,
yeah,
yeah,
weight fraction of
weight fraction of
A or B. Let's say
A
this
or
is
B.
my
Let's say this is my
B.
B.
We are talking about B,
We are
so
talking
it
about
will
B.
be my
So it will be
XB
my XB
automatically, right?
automatically,
So
right?
now
So now
XB in
XB
liquid,
in liquid,
or yeah,
or
XB
yeah,
in liquid
XB in liquid
times
times
K,
K,
or we call it as a
or we
partition
call it as a
coefficient,
partition coefficient,
equals to
equals to
XB
XB
S, or
S,
this will be
or
equals
this
to
will be equals to
XB S by
XB S by
XBL. Now
XBL.
why
Now,
I
why
use this
I use this
another constant term?
another constant
You will
term?
know it's
You
not a
will know
constant
it's not a
until
constant
unless our
until unless our
this the
this
slope
the slope
of this
of
solidus or
this
liquidus
solidus
line
or
is
liquidus
constant.
line is
If it
constant.
is
If
constant,
it is
then this will also
constant,
be
then this
constant.
will also be constant.
Right? If it is the
Right? If
slope
it
is
is the
varied,
slope
like
is varied,
it has
like
some
it has
parabolic
some
shape
parabolic
like this or
shape
like
like
this,
this or like
then
this,
this will not be a
then this will
constant.
not be a constant.
And for again
And for
to make our
again to
mathematics
make our
simpler,
mathematics
let's
simpler,
take this
let's
as a
take
constant.
this as a constant.
So this will become a
So this
constant.
will become a constant.
This will, so
This will,
assume this as
so
a straight
assume this
line.
as a
This will
straight
become a
line. This will
constant.
become a
Okay.
constant. Okay.
Now
Now,
the next step will be
the next step will be
the assumptions.
the assumptions.
What are the
What
assumptions?
are the assumptions?
See, solid
See, solid
has its own
has its
atoms,
own
right?
atoms, right?
And they have a
And they have
diffusion
a
coefficient,
diffusion coefficient,
right? Now next
right?
one,
Now, next
liquid
one, liquid
has its own
has its
atoms,
own atoms,
atomics, like
atomics,
atomic
like atomic
configuration, which
configuration,
is random.
which
But
is
solid
random,
there is
but solid there is
symmetry,
symmetry,
the crystallinity.
the
Now what
crystallinity.
about in
Now, what
liquid?
about in liquid?
Liquid, it's
Liquid,
amorphous,
it's
and
amorphous, and
there is also
there is
a
also
diffusion
a
coefficient
diffusion
related to
coefficient related to
liquid atoms.
liquid
Now
atoms.
we have to
Now,
define
we
this
have to
thing
define this
before
thing
we go into
before
this
we go
kinetics
into
part,
this
how the
kinetics
solid
part,
is
how
going,
the
how the
solid is
liquid is
going, how
going,
the liquid is
right?
going,
So
right? So,
our basic
our
assumptions
basic
start
assumptions
from here.
start from
The
here.
first assumption
The
is
first assumption is
what?
what?
ds
ds
is infinite,
is infinite,
which is not an
which is
ideal
not
case.
an ideal case.
dl is also
dl is
infinite.
also
That
infinite.
means
That means
there is a perfect
there is a
mixing in
perfect
liquid.
mixing in liquid.
What do I mean perfect
What do I
mixing?
mean perfect
Suppose if you
mixing?
have a pond
Suppose
of
if you have a
a
pond
bucket
of
of water, if
bucket
you
of water,
drop
if you
one
drop one
drop of
drop of
kerosene or
kerosene
methanol,
or
it will
methanol,
completely
it will
disperse in
completely
this bucket
disperse
of
in
water.
this bucket of
So that
water.
is called as a
So that is
perfect
called
mixing.
as a perfect mixing.
Now, what
Now,
about solids?
what about solids?
Let's take solid
Let's
has.
take solid has.
It's the equilibrium
It's the
solidification. That's
equilibrium
what we are doing.
solidification. That's what
Equilibrium
we are doing.
solidification
Equilibrium
means we are giving
solidification means we
enough
are
time
giving
for
enough
diffusion
time
to
for
take place.
diffusion to take
It's not
place.
like
It's
diffusion
not
is
like
infinite.
diffusion is infinite.
Let me make
Let me
changes.
make changes.
We can have two
Or we
cases.
can have
Like
two
we
cases,
can
like
say the
we
diffusion
can
is
say the
infinite, but
diffusion is
it is
infinite,
more
but it is more
non-ideality case. So let's
non-ideality
say
case. So let's say
for diffusion to
for
happens,
diffusion
we
to
are giving
happens, we are
enough
giving
time,
enough time,
right? Let's say
right?
diffusion
Let's
has
say
some
diffusion
constant
has some
k
constant
dash,
k dash,
and to
and
totally
to
diffuse
totally
the solid,
diffuse
for
in the
example,
solid, for example,
like here,
like here,
this is my starting
this is
point,
my
right?
starting point,
Let me take
right?
a different
Let me
color.
take a different color.
Suppose this is my
Suppose this is my
starting point.
starting
Okay.
point. Okay.
Now, at
Now,
here the
at
liquid,
here, the liquid,
let's say
at
at
let's
point
say
one,
at point one,
right? This is point
right?
one,
This is point one,
and it came to
and
here.
it came to here.
This is
This is point. This is
two.
point two.
Again, it came down
Again,
to
it
here.
came down to here.
This is point
This
three.
is point three.
Finally,
Finally, it came down to
this point four,
this
and
point four,
again
and again
point five.
point
Now, what
five.
is happening
Now,
when
what
it
is
is
happening when
at
it
point
is
one?
at point one?
Yeah, at
Yeah,
point one, what
at
is my
point one,
liquid?
what is my liquid?
Liquid will be equals
Liquid will be equals
concentration
liquid
will be equal to
concentration
x
will be
naught.
equal to x naught.
Now, what at
Now,
point two?
what at point two?
Just below,
Just below,
right?
right?
Let's say
Let's say
this is my
this is my
this is my
point one, right? Related to point two. It's not point one related to point
It
two.
has
It
a
has a
concentration
concentration
of
of
excess 2.
excess two.
Okay,
Okay,
that's
that's
not
not
excess.
right excess.
For solid,
For,
right?
for
Let's
solid, right? Let's
excess
write
2.
excess
Then
two.
what is my
Then
excel?
what is my excel?
Or let's say
Or let's say
what is my excel?
what is my excel?
Excel
Then
will be equals
excel will be equals
to
to
XS2
xs
upon
two
K.
upon k.
Right? We can get
Right?
those
We can
relations
get
from
those
this.
relations from this.
So that's what we are
So
doing.
that's what we are
Now,
doing. Now,
coming back to this,
coming back to
we
this,
are giving
we are giving
certification, equilibrium
certification,
certification.
equilibrium
That means we are
certification.
giving
That means we
enough
are
amount
giving
of
enough
time
amount of time
to
to
total
total
dissolution.
dissolution.
Right? So
Right? So
at point one,
at point one,
we had
we had
XL as a liquid.
XL as a liquid.
Right? Let's say
Right? Let's say
at time t
at
equals
time
to
t equals to
T1.
t1.
That means there is
It
still
means
total
there is
liquid.
still total
We
liquid.
arrived
We arrived
from
from
top
top
to here.
to here.
Okay?
Okay?
Then
Then that means
XL will be
XL
equals to
will be equals
X naught.
to x naught.
Now at
Now at
T equals to 2,
t equals to 2,
point P2.
point P2.
What is happening?
What is happening?
Liquid is getting
Liquid is
enriched,
getting
and
enriched,
solid.
and solid
Liquid gets
liquid
solid
gets solid
forms,
forms,
and
and
let's
let's
say
say the solid forms out.
what do we call?
What do we call?
Let's say solid
Let's
forms
say solid forms out
X2.
x2.
Okay?
Okay?
XS2.
xs2.
It forms at here.
It forms at here.
That
That
will be
will be equals to
K
k
XL.
xl.
Right?
Right?
Or you can say,
Or you can say, or you can assume any composition. Now, what happens at T3?
At T3,
At T3,
see,
the
concentration of the
concentration of
solute
solute
atoms
atoms in
is
B
increasing.
is increasing,
Right?
right? And also the concentration of B in liquid is also
So
increasing.
some part
So some part
will be rejected.
will be rejected,
Right?
right? So first it forms
excess
XS2. That means some amount of solute is being rejected into liquid. Then again, if liquid solidifies, some amount will again be rejected. So that's why
from X naught,
from x naught,
this is my X naught, right?
From x naught, the liquid concentration keeps on rising. Simultaneously, the solid concentration also keeps on rising.
So that is what happens.
So that is what happened here.
Right?
That is what we discussed last time in pouring. So keep the solid keeps on rejecting solute into liquid, and also liquids keep getting richer and richer, and again that liquid has to solidify also, right? So again some part of solid again reject some liquid, solute into liquid, and again the liquid gets richer. So that's how
this whole process
goes on.
And please keep
remember, in coring we didn't discuss complete solid, we didn't give enough time to get solidified. That's why we had
a concentration gradient
throughout the sample.
But
what now we are going to do is, let's say if we take a coring type phenomena, that means from periphery to center, the concentration of solute atoms is increasing. Now what if you give enough amount of time for diffusion to happen? So let's say I keep this sample in a furnace. Okay. Now what happens?
If
If
I
I
keep
keep
this
this
sample
sample
in
in
the
the
fun
fun
lens,
lens,
again
again
you
giving enough amount of time energy for
solid atoms to
solid
diffuse.
atoms to
So
diffuse.
they
So they
will tend to
will
diffuse
tend to
from
diffuse
higher
from higher
concentration to
concentration
lower
to
concentration.
lower concentration.
Let's we are only
Let's
talking
We are
about
only talking
downhill
about
diffusion. Let's
downhill
not talk about
diffusion. Let's
uphill
not talk
diffusion.
about uphill
We are
diffusion.
only talking
We
about
are
some
only talking about
isomorphic diagrams,
isomorphic
right?
diagram, right?
So
So
then what happens?
then what
So
happens?
these
So
atoms,
these atoms,
because of this
and because of
concentration
this
gradient,
concentration
the
gradient,
atoms will
the
diffuse from
atoms will
higher
diffuse from
concentration to
higher
lower
concentration to
concentration.
lower concentration.
And
And
finally,
the
after
finally,
giving enough
after
amount of
giving enough
time,
amount of
this
time,
whole
this whole
concentration will
concentration
become
will
average out.
become average
So
out.
finally,
So
you will
finally,
have the
you will
average
have the average
composition
composition
will
will
be
be
x0.
X naught.
So that is the
So
case
that is the
here.
case here.
Okay.
Oh, okay.
So that is the case
So
here.
that is the
That
case
means we
here.
are
That
giving
means we are giving
enough amount of time.
enough amount of time.
That's why we
That's
called
why
it
we
as
called it as the
the equilibrium
equilibrium
solidification.
solidification.
Right. At every
Right.
point we
At
are
every
giving enough
point we are
amount of
giving
time
enough
so that
amount of time
the
so that
atoms can
the
diffuse and
atoms can
average
diffuse
out
and average out
that composition
that
inside the
composition
solid.
inside the
So
solid.
that is why
So
we
that is
see
why we see
it has
it
a
has
constant
a
line,
constant
right?
line, right?
Throughout the solid,
Throughout the
the
solid,
concentration
the
is
concentration
whether
is
it is
whether it
excess
is
or between
excess
x
or
naught or
between X
excess.
naught or excess.
That's all.
That's all.
Now,
Now,
if we try
if we
to
try to
if we try to know
if we try to
how
know
it is
how
rejecting,
it is rejecting,
let's take
let's
what
take
is this?
what
Let's say
is
this
this?
is
Let's say this is
total is
total
L
is L,
and this is my
and this is my
x. Okay.
X. Okay.
Now, what is
Now,
this area?
what is this area?
Thickness into
Thickness
width.
into width.
That will be
That will be
x naught
X naught
minus
minus
xs
XS
upon,
upon,
oh sorry,
oh sorry,
it will be
it will be
times
times, not
upon
upon,
cross
cross
x.
X.
That will be
That
equals
will
to
be equals to
x naught
X naught
minus,
minus, or you can say
xl
XL
minus
minus X naught
upon
upon,
times
not times
L minus x.
L minus X.
Right, these two areas
Right,
must
these
be
two
equal
areas must be equal
because
because
that tells me
that
the,
tells me the the
conservation of
conservation
mass,
of mass,
because there is no
because
escape
there
of
is no
mass here.
escape of mass here.
So that's what it
So
tells
that's
me.
what it tells me.
Right, they
Right,
must be equal.
they must be equal.
Now,
Now,
x.
X.
If I do this,
then if I take X naught minus XS
divided
divided
by
by XL minus X naught,
that will be
that
equals
will be equals
to
to
L
L minus
L
L
by
by
x
X
minus 1.
minus 1.
Right. Now,
Right? Now,
if I take
if I take
if
if
I
I
want
want
to
to
take
take
out
out
x
X
naught
naught
as
as
a
a
common,
common, let's say
that is a
that
constant,
is a
then
constant, then
xs
XS
will
will
be
be
equal
equal
to
to K
k xl.
XL.
If I substitute that
If I
there,
substitute that there,
then
then
x naught
X naught
minus k
minus K
xl
XL
upon
upon
xl
XL
minus x
minus
naught
X naught
equals to
equals
L
to
by
L
x
by
minus
X
1,
minus 1,
and that will be
and
equals
that will
to,
be equals to,
if I take
if
minus
I
1
take
as a
minus
common,
1 as a
then this
common,
will be
then this will be
1 minus
1
k
minus K equals to
or
or
minus
minus
L by
L by
x minus
X
1, or you
minus
can
1,
take it
or I
as
can take it
k
as
minus
K
1
minus 1
till
till equals
L
to
by
L
x
by
minus 1.
X minus
So
1.
k will
So
be
K
equals
will
to
be equals to
what?
what?
L by
L by
x.
X.
Right, so this is our
Right, so
relation.
this is our relation.
Finally, you will arrive.
Finally, you will arrive at.
Right, so this is a
Right,
simpler
so this
one.
is a simpler one.
We do not have
We,
to
we
do
do not
any
have to do any like more
calculative thing here.
calculative thing
It
here.
is very simple.
It is very simple.
Right?
Right?
Now,
Now,
let me have one more slide. Now,
coming
the
to
next part.
the next
The
part.
next part is,
The next part is
what are assumptions
what
again?
are assumptions again?
Before we had
Before
the
we
assumption
had
like
the assumption like Equilibrium solidification, that means giving enough time for solid to like average out its composition, right? So these are our assumptions. Now coming on to
the second one.
the second one.
The first one
The
is
first one
again
is again
complete
complete
mixing in liquid.
mixing in liquid. Hmm?
There is step
This
one,
is step
the
one
assumption one.
or the
The second
assumption
one
one.
is
The second one
there
is
is no
there
diffusion.
is no diffusion in
Solid,
liquid.
sorry.
Solid, sorry.
There is no
There is no
diffusion
diffusion
in solid.
in solid.
Let's say we are
Let's
quenching.
say we are
Instead
quenching.
of cooling
Instead of cooling
the solidified
the
part,
solidified
let's
part,
say instead of
let's
cooling
say
this
instead of
solidified
cooling
part,
this
we are
solidified
quenching
part,
this
we are
solidified
quenching
part.
this solidified part.
Then we are completely
Then we are
arresting
completely
the
arresting
thermal
the
motion of
thermal
atoms,
motion of
the
atoms,
diffusion of
the
atoms.
diffusion of
Right?
atoms.
So
Right?
that is what.
So
That
that
is
is what.
this.
That is this.
What does it? What does
What
this
does it?
mean?
What does this mean?
Means the diffusion is
Means the
zero.
diffusion is zero.
Diffusion of atoms
Diffusion of atoms
in solid
in solid
is zero.
is
There
zero.
is no diffusion
There's
of
no
atoms
diffusion
in
of
solid. That means
atoms
we
in
are
solid. That
quenching it.
means we are quenching it.
Right? So
Right?
that's how we are
So
going
that's
to
how we
assume.
are going to assume it.
Now, if
Now,
that is the
if
case,
that is the case,
right, then how
right, then how
we are going
we are
to
going to
right?
right?
How how
How
do we know
how do we
the
know
excess
the
or the
excess
mole
or
fraction
the
or
mole
the weight
fraction or
fraction
the
of
weight fraction of
not the weight fraction
not the weight
or
fraction
the weight
or the weight
the solute
the
fraction
solute fraction
in solid is going
in
to
solid
change.
is going to change,
Right? So that is
right? So
what we
that
want
is
to
what
try
we
and that
want
is
to
what we
try,
want
that
to
is
try
what we
here.
want to try here.
Now,
Now
you can see
you can see
at the beginning
at the beginning, yeah,
you can see at the
you can
beginning
see at the beginning
here we
here
have only
you
liquid.
have only liquid.
Now once you
Now once you
came down a bit,
came down a bit,
the solute
the solute
the liquid keeps on
the liquid keeps on
the
reject
solid
the solid
keeps on
keeps
rejecting
on rejecting
the
the
solute into the liquid,
solute into the
right?
liquid, right?
So let's say
So
let's take the
let's
first
take
one.
the first one.
Let's say
Let's say
this is the amount of
this is the
solid that
amount of
has
solid
formed
that has formed
at time t
at
equals to
time
t1,
t equals to t1,
right?
right?
Now this is my
Now
liquid.
this is my liquid.
Now my solid
Now
has
my
rejected
solid
some
has
part
rejected
of the
some part of the
solute into the
solute
liquid.
into the
Now
liquid.
liquid
Now liquid
concentration
concentration
has risen by a
has
value,
risen by a
let's say
value, let's say
XL1.
XL1.
Now this,
Now
the
this,
next part that
the
is
next
going to
part that is
solidify,
going to solidify,
right? It's
right?
not like we are
It's not
fixing,
like we are fixing, we are
quenching more and more.
quenching
That
more and
means
more. That means
the part
the part
or the part that is
or the
very
part that is
adjacent
very
to the liquid
adjacent to the
is going
liquid
to
is
solidify.
going to
So this
solidify.
part is going
So
to
this part is
solidify.
going to solidify.
But
But
keep
keep
in
in
mind
keep in
that
mind
before
that before
the solidification
the
of this part,
solidification of this
the
part,
liquid
the
the
liquid
liquid has
the
let's say
liquid
the
has
liquid
let's say
has
the
a
liquid has a
concentration of XL1,
concentration of
the
XL1,
solid has a
and the solid
concentration
has a
of
concentration of
XS1.
XS1.
Now the liquid
Now the
concentration
liquid concentration has
because
increased
of this
because
solid.
of this solid.
This part
This part has more
concentration of B atoms
concentration of
than
B
solid.
atoms than solid.
So
So
when this part gets
when this part
solidified,
gets solidified,
it
it has concentration
XS2
XS2
more than XS1.
more than XS1.
And now because this
And now
part has
because this part
solidified,
has solidified,
some
some
part
part is going to
reject into the
reject
liquid.
into the liquid.
Now
Now
the liquid has
concentration
concentration XL2.
XL2.
Right, it's not like
Right,
whole
it's not like whole part
XL1
XL1
some part of XL1
some part of
is
XL1 is going to solidify into
XS2, right?
XS2,
Some
right?
part of is going
Some
to
part of is
rejected by
going to
the solid.
rejected by the
So
solid.
that is what we
So
are
that is
seeing
what
here.
we are seeing here.
So
So some part is going to get rejected,
right? So that's what
right?
happened.
So that's what happening.
Now
Now
again
again
this
this part
part
is going to solidify.
So
So
XS1
XS1
XS2
XS2 we will have XS3
and they will have
and they will have
XL3.
XL3.
That
That
means
means the liquid concentration keeps on increasing and the solid concentration also keeps on increasing, but it will not have an equilibrium concentration like
here.
here.
right? We are not giving enough time to totally diffuse the atoms in the solid. So that's why it will take a different path in this diagram depending upon cooling. Right, so that is what we see here. Now, how do we give an explanation to how this excess is going to change, or excel is going to change with respect to the solidification? Right? Now let's do that. Now, let's say a part of solid has formed. That means the fraction of solid that has been formed, the fraction of solid that has formed, times what is the concentration of that solid. That means XL minus XS. Right? That is the concentration of solid that has been formed. That will be equals to what is the concentration in liquid that has been formed into solid. That will be dxl. This is the change in the liquid because of the solidification. Right? Some part of solute is being rejected into the liquid. So that will be equals to 1 minus Fs. Right? That will be Fl. So we are writing 1 minus Fs. Now, this is our differential equation. Now, how do we solve it? To solve this, we need to have what? The boundary conditions. To solve any differential equations, we need boundary conditions. Now, what are boundary conditions? Initial point. Right. What is our initial point? At Fs equals to 0, we have a boundary condition. Xs equals to Kx0. Right? Xs equals to Kx0, where x0 is my liquid concentration at the first point. Now, let's do this one. So we know Xs equals to Kxl. This is one thing we have assumed the partition equation coefficient, right? Now if I substitute that thing here, so Xs will be XL minus KXL. This will be my DFS. Now we will have DXL 1 by Fs. Now if I divide both sides by DFS, and if I take it this term here, then this, and I take out, let's do it one step at a time. XL minus KXL upon DXL 1 minus Fs upon DFS. Let's invert both sides, then this will turn out to be DXL XL minus KXL equals to 1 minus, sorry, DFS of 1 minus Fs. Right? Now if I take XL outside, then I will remain with 1 by 1 minus K, and I have ln XL will be equals to ln 1 minus Fs. There will be minus 1. Right? Yeah, there should be minus 1. So, or you can take it as minus 1 here. In fact, let me remove it. This will be more. This will minus will be taken by this one. So this will turn out to be 1 by K minus 1 ln XL ln 1 minus Fs. So this will go that side. If I keep this one here, then XL will be equals to ln 1 minus Fs K minus 1. Right? We know A ln B will be equals to ln B power n. This is the identity I have used. Then here's the thing we have remind with, and we also know what is XL. XL equals to XS by XL equals to XS by K. Right? Yeah. I'm substituting that XL equals to ln 1 minus Fs K minus 1. XL will be equals to XS upon K. It will be equals to ln 1 minus Fs K minus 1. This will be equals to XS is equals to K ln n 1 minus Fs K minus 1. So this is our relation for to know how this change is going to happen. Access is going to change to happen. Now to we forgot to mention there we have a constant. Right? We also have a constant K1 because we didn't do uh, exact differential, right? So that's why we'll have a K1 here. Now if you substitute at Fs equals to 0, XL equals to X0, right? Then what happens? XL will be equals to K1 ln 1 minus 0 upon K minus 1. So this will go away. Then the XL will be X0 will be K1. That means XL equals to K X0 1 minus Fs K minus 1. Right? So that is the relation, that is the final relation. Right? So K1, then you will substitute and you will get that equation. Now, that is about these terms. Now let's see the third case. Right, now this is how you will get what is the excess, right? This is excess. This is how the excess changes with respect to the fraction of solid that has been converted into liquid. Right? Now the third case where the assumptions are taken a little bit different. Okay? Here my assumptions are assumptions no, it's a different one. Yeah, these I should write here. My assumptions part 3. Right? Now what are my assumptions here? First, diffusion in solid is 0. right? That is ds is 0.
And in liquid,
And in liquid,
we are
we are
assuming
assuming
the concentration
the
gradient.
concentration gradient. Concentrate.
Right, so this is our
Right, so
second
this is
case.
our
That
second
means we
case.
are not
That means we are
allowing a
not
perfect
allowing a
mixing
perfect mixing
in the liquid.
in the liquid.
Right, if there is
Right,
no
if there
stirring
is no
or a
stirring
convection
or a
in the liquid
convection
phase,
in the liquid phase,
then the
then
solute
the
rejected.
solute rejected.
Right, so
Right,
solute
so the solute
gets rejected.
gets rejected. So
That's right.
that's
So
right.
this is my interface.
This is my interface. This is my solid. This is my
Now
liquid.
once the solute
Now once
forms,
the solute
it
forms,
rejects
it
the solute
rejects the
on the
solute
liquid side,
on the liquid
and
side,
because of
and
that,
because of that,
and there is no
and there is no
convection or there is no
convection or
perfect
there is no
mixing
perfect
in the liquid,
mixing in the
and
liquid,
so
and
because of
so because of
this case,
this case,
all the
the
solute
all the
will come
solute
out
will come out
at the
at the
interface.
at the
So that's why
interface. So that's
we'll have
why
a
we'll have a
concentration gradient
concentration gradient
in the liquid
in
phase.
the liquid phase.
Right. So this is
Right.
my
So this is my
C
C
versus X.
versus X.
So there is our
So there is
concentration
our
gradient
concentration
in the
gradient
liquid phase,
in the
and
liquid phase,
also
and also
this
this
interface is moving.
interface is moving.
Right. So
Right.
this
So
interface is
this
moving.
interface is moving.
Now how do we
Now how do we
now how do we derive
how
a
do we derive
mathematical
a
relation to
mathematical
this
relation to
movement
this
of this
movement
interface?
of this
So how fast
interface?
the
So how
interface is
fast the
going to move?
interface is going to move?
That is our question.
That is our question.
Let's derive how
Let's
it is.
derive how it is.
So
So mm,
here there will be
here there
a
will
so
be
because
a
of
so
that
because of
there will
that
be a rapid
there will be a
buildup.
rapid buildup.
Right. There is a
Right,
buildup
there
of
will be a
solid
buildup of solid
in the liquid.
in the liquid,
And this is also
and this is also
known as
known as
initial transient.
initial
Now,
transient.
if
Now, if
solidification is
solidification
made
is
to occur
made to
at a
occur
constant
at a
rate,
constant rate, for
if we are
example,
cooling
if we
at
are
a
cooling
constant
at a
rate,
constant rate,
then
then
this
this
interface
interface
will
will
also
also
move
move
with
with
a
a
constant
constant
velocity
velocity
v,
v.
right? If you
Right?
are trying
If
to
you are trying
cool it very
to
fast,
cool it
then
very
this
fast, then this
velocity front will also move very
velocity front
fast.
will also move very
If you are
fast.
trying to
If you are
slowly
trying to
take out the
slowly
heat
take out the
from a
heat
side,
from a
then
side,
this
then this
velocity
velocity
front will
front
also
will
move
also
at
move
a
at a
constant
constant
what do you call it?
what
At
do
a
you call
constant
at a
speed,
constant
right?
speed, right?
So
So
now
now
so at one
so at one so
that means
that means
if it is moving at a
if it is
constant
moving at a
speed,
constant speed,
we are there
we
is
are
that means there
there
is
is
no
that means there is
acceleration.
no
That means there
acceleration.
is no
That means there is
acceleration.
no
Then again
acceleration. Then
we are
again
achieving
we
a
are
steady
achieving
state.
a steady state.
So that is what
So that is
we
what
have
we have
shown here. So
shown
we
here.
are achieving a
So
steady
we are
state.
achieving a steady state.
So the liquid
So the liquid
yeah.
yeah.
So the liquid
So the
adjacent to
liquid
the
adjacent to
interface
the
temperature
interface temperature
reaches T3.
reaches T3.
Yeah. The liquid
Yeah. The
adjacent to
liquid
the solid
adjacent
then
to the
has a
solid then has a
composition.
composition.
So
So
XL will be
XL will be
X naught upon
X naught
K.
upon K.
Right. If this
Right.
is my
If this is my
transient zone where
transient
the
zone where the
solid has
solid has
reached
reached
X naught,
X naught,
right?
right?
Then that will be
Then
equals
that will
to
be equals to
XL will be X naught
XL will
upon
be
K.
X naught upon
Now
K.
during this
Now,
steady
during
state
this
growth,
steady state
the
growth,
concentration
the
profile
concentration
in the
profile
liquid
in the liquid
must be such that
must be such
the
that
rate at
the
which
rate at
the
which
solute
the
diffuses
solute
down
diffuses
the
down the
concentration gradient
concentration
away from the
gradient away
interface
from the
is
interface
balanced
is
by the
balanced
rate at
by the
which the
rate at
solute
which the
is
solute
rejected
is
from the
rejected from the
solidifying
solidifying
liquid,
liquid.
right?
Right?
Now,
Now,
let me
let me
explain this.
explain this.
So, as
So,
I've said
as
before,
I've said
we
before,
are
we
achieving
are
a steady
achieving
state.
a steady state.
That means
That means
at first
at
there is a
first
liquid
there is a
solid.
liquid solid.
There is an increase in
There is increase
concentration
in
of a solid,
concentration of a
then
solid,
it reaches
then it reaches
a
a constant
value, right? So
value,
this is my
right?
x
So this
naught,
is my
and
x
let's say
naught,
this is my
and let's say
kx
this is
naught,
my kx
and
naught,
this
and this
interface
interface
is moving.
is moving.
That means we
That
have
means
again we have a
we have
concentration
a
gradient,
concentration gradient
and
here.
this is my
And this
concentration
is my
gradient.
concentration
And
gradient.
what
And
the
what
steady state
the
mean
steady state
is,
mean
so
is,
this x
so
naught
this
will
x
remain
naught
the
will
same.
remain the
That
same.
means
That means
whatever the solute
whatever
atoms
the
that
solute
have been
atoms that have been that are being
uh,
uh,
diffused through
diffused
this
through
diffusion,
this diffusion layer,
this boundary
this
layer
boundary layer
must be equal
must
to
be equal to
the rejection
the rejection
from the solid.
from the solid.
This is the solid
This
part
is
that
a
has been
solid part that has
transformed.
been transformed.
So the
So
rejection
the
must be
rejection
equals
must
to
be
the
equals to
diffusion of
the
solids.
diffusion of
The
solids,
diffusion of
the diffusion
solid
of
atoms
solid
across this
atoms
interface.
across this interface.
Suppose if
Suppose if
the solid is
the
keep on
solid is
rejecting,
keep on
then
rejecting,
the
then
speed
the
or the,
speed
the
or
speed with which
the
the
speed with
diffusion
which the
atoms are
diffusion
not
atoms are
diffusing
not diffusing
well,
well,
then
then
this buildup will
this
increase,
buildup will increase,
right? And the part
right?
of the
And the
solid
part of the
that's
solid
going to
that's
solidify
going to
will also
solidify
get
it will
increased,
also get increased,
right? To
right?
achieve this
To
steady state,
achieve this steady
this is
state,
our assumption.
this is our
Now,
assumption. Now,
again,
again,
so the diffuse
so the diffuse
or the solute atoms
or
that
the
have
solute
been
atoms that have
diffusing
been
down
diffusing down
this concentration
this
gradient
concentration
or away
gradient
from the
or away
interface
from the interface
must be balanced
must be
by the
balanced by the
solute atoms that has
solute
been
atoms that
rejected.
has been rejected.
Right? Now,
Right.
how do we write
Now,
the
how do we
flux
write the
of
flux
an atoms
of an
that has
atoms
been
that has been
coming
coming
down
down
to
to
this
this
concentration
concentration
hill
hill will be equals
will
to
be equals to
minus d
dou C
dou c
by dou
by
x or
dou
dou
x
Cl
or dou cl
inside the liquid.
inside the
So
liquid.
this
So this
must be equals
must
to
be equals to
the velocity front.
the velocity
That will be
front.
equals to
That will be
times
equals to
V,
times v,
which will be Cl
which will be
minus
cl minus
Cs. So that
cs.
is
So
the
that
amount
is
of
the
solute
amount of solute
that's been
that's being
spit out,
spit out,
right?
right?
So
So
now,
now,
where here the
where
D is
here
what
the
the
D is what
diffusivity
the
in liquid,
diffusivity in liquid,
and
and
Cl minus
Cl
Cs
minus
means the
Cs means the
concentration that means
concentration that
rejected
means
into the
rejected
liquid.
into the liquid.
Now, if you
Now,
try to
if you
solve
try to solve
this equation,
this equation,
right?
right?
So we will
So
have,
we will have,
or we can even
or we
solve
can even solve
another
in
form,
another form,
right?
right?
How do we solve that?
How do we solve that?
So
So
dou C by dou
dou
T,
C by
dou
dou T,
Cl
dou
by dou T
Cl by dou
will
T
be equals to
will be
minus
equals
D
to minus
dou
D
square C
dou square
upon dou
C
x square.
upon dou x
If
square. If
this
this
front is at a
front
constant,
is at a constant,
what if it is
what
moving?
if it is
Then we will
moving?
have
Then we will
dou
have
C upon dou
dou
x,
C upon dou x,
right?
right?
And if we are
And if
achieving
we are achieving
a steady state,
a steady
then this
state,
will be equals
then
to
this will
0.
be equals
So
to
we can
0. So
equate
we
this
can
to
equate
0.
this to
Then we
0.
will have
Then we will have d
d square
d square
plus v
plus
d
v
equals
d
to 0.
equals to 0.
Then we will
Then
easily
we will
arrive
easily arrive
to the empirical
to the
formula
empirical formula
a
a
exponential
exponential
minus x
minus x
d by v
d by v
plus b.
plus b.
Right, again,
Right? Again,
at
at first,
at
at
fs equals to
fs
0,
equals to 0,
xl equals
xl
to
equals
x
to
naught.
x naught.
And if we substitute
And if we
that, then
substitute that, then
finally
we'll
will
finally will
remain with
remain with
xl into
xl into
x naught
x naught
plus
plus
1 minus
1
k
minus
upon
k
k
upon
into
k
x naught
into x
into
naught into
exponential
exponential
minus x
minus
upon
x upon
dv.
dv.
Now, again, if I
Now,
take
again, if I
few
take
things
few
common,
things common,
then
then
xl will be
xl will be
x naught
x naught
upon 1 plus
upon 1
1
plus
minus k
1 minus k
upon k
upon k
times
times
exponential
exponential
minus x
minus x
upon
upon
dv.
dv.
So
So
there is our
our
another relation
another
for
relation for solidification
for
or
this
for this
assumption,
assumption,
where
where
we
we
have
have
diffusion
diffusion
in
in
solid
solid
will
will
be
be
equals
equals
to
to
0,
0,
but
but
we
we
have
have
liquid.
liquid.
There
In
is a
liquid there is
concentration
a
gradient. That
concentration
means there
gradient.
is no
That means
perfect
there is no
mixing
perfect mixing
inside a liquid.
inside a liquid.
So that is our
So
relation.
that is our relation.
Now,
Now,
This is about
this is
the
about
diffusion of
the
atoms.
diffusion of atoms.
Now coming to the alloy
Now, coming to the
solidification.
alloy solidification.
Right. Now,
Right.
so far we have
Now, so
seen
far we have seen
how
how
if the
if
diffusion
the diffusion uh,
in solids and
in
liquids
solids and
hinders
liquids hinders
the type of
the type of
the Excel
the
equation or
Excel
the Excess
equation or the
equation is
excess
going to
equation is
change,
going to change.
right? Now
Right.
that is about
Now, that is about
those part.
those
Now
part.
coming to
Now, coming to
the alloy
the
solidification.
alloy
Now in
solidification.
alloy
Now,
solidification
in
is
alloy
also
solidification is
the
also
role of
the role
the
of
diffusion of
the
solid and
diffusion
liquid
of solid
atoms.
and liquid atoms.
But also there
But
is one
also
thing
there is one
in,
thing in,
let's say, in pure
let's say, in
metals
pure metals
we have seen
we have seen
the thermal gradients,
the
right?
thermal
This is one
gradients, right?
thermal
This is
gradient.
one thermal
Then you
gradient.
will have
Then we
the
will
planar
have the
interface.
planar
Now
interface.
if we have a
Now, if
thermal
we have
gradient,
a
this is
thermal
solid,
gradient,
this
this
is
is
liquid.
solid, this is liquid.
And if you have a
And if
thermal
we have a
gradient like
thermal
this,
gradient like
then
this,
you will have
then
you have a planar
you have a
interface
planar
here,
interface here.
but here you have
But here you have
columnar one,
columnar form.
right? Or
Right. Or
if you have
and if you have
if we
if
satisfy this
we
condition,
satisfy this
we will have
condition, we will
dendrite
have
formation
dendrite formation
here, right?
here.
So
Right.
we
So
also
we
call them
also
as
call them as
thermal dendrites,
thermal dendrites.
right? So
Right.
these are
So
this
these
we
are
have seen
this we
in
have
pure
seen
metals.
in pure metals.
Now what
Now,
happens
what
if we
happens
have
if we have
an alloy?
an alloy?
What about dendrites
What
will
about
form?
dendrites will form?
We There is
We
another
There
term
is an
which
another
will come
term
into
which will
picture.
come into
Here
picture.
it is. We
Here
have
it
seen
is. We have seen
undercooling,
the
the surface
undercooling, the
undercooling
surface
because of
undercooling, because
if
of
there is a
if
formation
there
of
is a
another
formation
surface,
of another
we have
surface,
to cool
we
down
have to
more,
cool down more.
right?
Right.
We have seen if
We have seen if
that's what we have seen in
that's what
previous
we have
lectures,
seen in
right?
previous
The
lectures, right?
first one
The
is
first
the
one is
volumetric
the
undercooling, right?
volumetric
Because of
undercooling, right? Because of
GV, GL
GV,
minus GS,
GL minus GS,
right? This
right?
will
This
give
will
the
give
change, the
the
transformation
change,
of
the
solid to
transformation of
liquid
solid to
will give you
liquid will
the
give you
volumetric free
the
energy,
volumetric free energy,
and that will
and
be
that
used
will
by
be
the
used by
surface
the surface
formation.
formation.
That's why we have to
That's why we have
undercooling
to
to get
undercool it to get
the solids.
the
Now there is
solids.
another
Now,
type of
there is another type
undercooling,
of
that
undercooling,
is
that is
constitutional undercooling.
constitutional undercooling.
Constitutional
Constitutional
undercooling,
undercooling.
or you can call it
Or
as
you can call it
supercooling.
as supercooling.
Right. So this
Right.
is the
So
another
this
type
this
of
is the another type of
undercooling, the constitutional
undercooling, the
undercooling,
constitutional
which I
undercooling,
will
which I will
explain
explain
in
in
in few minutes.
in few minutes.
Right.
Right.
So
So
yeah,
yeah,
let's say
let's say
this is my
this is my
solid
solid
and this is my
and this is my
liquid.
liquid.
We have a solid
We have a solid
and liquid,
and liquid.
right?
Right.
Now,
Now,
just
just
let me
let me
write how
write how
this concentration is
this
going to
concentration is
change.
going to change.
So
So
let's say
let's say
this is my
this
solid
is my solid
and this is liquid.
and this is liquid.
Now, if some
Now,
amount of
if
solid
some
is
amount of
being
solid is being
rejected in liquid,
rejected in
right?
liquid, right? Now,
let's say this is
let's
my
say this is my uh,
temperature gradient
temperature
in liquid.
gradient in
Let's say
liquid.
this is my
Let's
temperature
say this is
gradient.
my temperature gradient.
Okay.
Okay.
Let's say this is my
Let's say
solid.
this is my solid.
This is my solid
This
and
is
this
my
is my
solid
liquid.
and this is my
And this
liquid.
is my thermal
And this is
gradient
my
in
thermal
liquid.
gradient
There
in
is no
liquid. There
diffusion
is
in
no diffusion in
solid. So
solid.
let's take
Let's
this as
take
our
this as
condition.
our condition.
And this is my
And this is my
liquid.
liquid.
Okay. Now,
Okay. Now,
this is my liquid.
this is my
So,
liquid. So,
for example,
for example,
at one point,
at one point,
more number of atoms
more number of atoms
came here,
came
and
here
it forms a
and it
protrusion.
forms a
Let's
protrusion.
say
Let's
it
say
has this
it
the
has
solid
this
liquid
the solid
interface has
liquid
formed a
interface has
protrusion.
formed a protrusion.
Now here
Now
the
here
temperature
the
is
temperature
higher,
is higher,
right?
right?
The temperature is
The
higher.
temperature is
But
higher. But
let's say
let's say
this.
this
Let's say this is my T1,
T1
and this is my
and this is my
T2,
T2,
this
this
is
is
my
my
T3.
T3,
Right now,
right? Now,
solid has a
solid has a
solid fraction
solid
or the
fraction or
concentration
the
as
concentration
excess
as
one,
excess one,
and it has
and
rejected
it
some
has
part into
rejected
the
some part
liquid.
into the
So
liquid.
because of
So
that,
because of that,
there is a
there is
concentration
a
increase in the
concentration increase
concentration
in the
of
concentration of
liquid.
liquid.
Now,
Now,
this liquid,
this liquid,
now this part
now this
will get
part
transformed,
will get
right? This part
transformed,
has
right? This
transformed
part
into
has transformed
again
into
solid.
again solid.
So it
So
has
it
a more
has a more
concentration
concentration
excess 2.
excess 2.
So
So
excess
excess
2
2 greater than
excess 1.
excess 1.
Right. Now,
Right. Now,
let's say
let's
if
say if
XS2
XS2
is stable
is stable
at T2,
at T2,
then
then
this will survive.
this will survive.
But in
But in
thermodynamics, we have
thermodynamics,
seen
we have
if
seen if
this is my T2,
this is my T2,
we know the pure
we
metal
know
is
the
not
pure
stable
metal is
above
not
the liquid
stable above the
melting
liquid
temperature.
melting temperature.
Right.
Right.
In thermodynamics.
In thermodynamics,
That's what we have seen.
that's what we have seen.
The pure metals
The pure
do not
metals
survive
do not survive
above melting temperature.
above melting
But
temperature.
here
But
is the case.
here is the case.
So that's what we are
So
seeing
that's
here.
what we are seeing
Here
here.
is the case.
Here is the
Where
case
XS2
where
is stable
XS2
at
is
temperature
stable
T2.
at temperature T2.
That means it can
That
survive.
means it can survive.
So
So
this
this
protrusion
protrusion will survive.
will survive. Now, if
Now,
suppose
if
it tries
suppose
to
if
grow,
it tries to grow,
so again
so again
it will have an
it will
existence.
have an
Again,
existence.
will it be
Again,
stable?
will it be
So
stable?
for
So
that
for
we
that
have to
we
draw
have to draw
our
our
the first one.
the first one. We have what the thermal
inside
gradient
the liquid.
inside the liquid.
The next one
The next
is
one
the
is
equilibrium
the
temperature
equilibrium
of the solid.
temperature of the solid.
Right.
Right. So let's say
This is my interface.
this is my solid.
This is
This is
my liquid.
my liquid.
Right.
Right. Now, this is solid. This is my liquid. Right. Right. This is my solid and this is my liquid. Now, this is my solid and liquid. Now, this is my thermal gradient. T dash. What is my equilibrium temperature? Right, the equilibrium solid temperature. Let's say if it goes like this.
Okay.
Okay. Now, what will happen here? If we have a case like this, that means whatever the solid that has been formed,
What are the solid that has, this is the equilibrium. This is my, let's say, let me erase this part. Yeah. So this line is my actual thermal change with respect to x, or the distance. This is my distance into the liquid, right? Now this is my equilibrium solidus temperature with respect to, again with respect to x. And because the concentration of liquid is keep on changing, so our if suppose there is a perfect mixing, even there is a, if suppose there is a perfect mixing, the composition of liquid keeps on changing. So that means the equilibrium solidus line will also change, right? So that is what we see here. Let me take to this phase diagram initially. Yeah, you can see here. If XL keeps on changing, then XL also will keep on changing, right? At this temperature, let's say at this T4 temperature, this is stable. Let's say at T2 temperature, this is stable. So that is what happening here, right? And that's what we see. And if the equilibrium temperature is higher than this, that means below this equilibrium temperature, that solid is stable. That's how you will have a dendrite formation there. That is what we call as a constitutional undercooling. Because of the addition of this element, there is an undercooling there. Right? Actually, the this protrusion shouldn't be stable here because of this constant increase in temperature. But because of the introduction of a solute, our equilibrium solidus temperature has changed. And because of this change, there is an undercooling. Right? This is my undercooling, right? This is the undercooling that's been provided here. And because of this, these will grow. And this is called as constitutional under cooling. And for constitutional undercooling to happen, what are the three things that we need to know? Right? And because of this, at this point, let's say this, we are trying about concentration here, and we are drawing temperature versus x, right? So and because of the rejection of solute, we will have it build up, and there will be a concentration gradient, right? So if you, this is the XL, now what about the temperature? The equilibrium temperature is like this, and our thermal gradient is like this, right? Now, how do we relate these two things, right? Again, if we talk about the steady state growth, like we start about, we discussed back in the previous assumption, under the steady state growth, right? The steady state growth, the critical, let's take the critical gradient, or this gradient, the temperature gradient, the temperature gradient TL dash, right? Should be less than or greater than or be equals to T1 minus T3. This is my temperature. This is, let's say, this is my T1. This is my T3 upon D by V. Right, so T1 minus T2, T1 minus T3 upon d by b. So this TL dash for a planar interface, for a planar interface, this must be greater than this. That means, what does that mean? That means, for example, if I draw this again, this is my equilibrium concentration. Then if this TL dash is greater than that, then so this is what it means. To have a planar interface, if we maintain a sharp thermal gradient inside the liquid, then we can avoid gel dendrite formation. So this is what it means. So the TL dash must be less than T1 minus T3 upon d by b. Then you will have a planar interface. If TL dash is less than T1 minus 3T upon d by b, then we will have the dendrites or columnar one, columnar structure. Right. Now again, the next part is the arms that has been brought. See, once we form a columnar region like this. So the solute is rejecting, not only rejecting from this side, the solute has been rejecting from the sideways also, right? So that's why there is a buildup of solute here, more here because of it is rejecting from the both sides. So again there will be formation of arms, and again there is a rejection. Again there is a formation of tertiary arms. So this is our primary dendrite. These are our secondary arms. Again, you will have tertiary arms. So depending upon what is our cooling rate, this spacing, the primary arm spacing, the secondary arm spacing can be defined depending upon our cooling rate, delta T upon delta T. This is change in temperature upon change in time. So this is about the cooling rate. This tells us about cooling rate, and it defines our arm spacing of dendrites. Right now, moving on to another type of, let's talk about another type of solidification, which is eutectic solidification. Let's talk about the eutectic solidification. Eutectic, right? Eutectic solidification. Eutectic solidification. So, we know, let's draw a eutectic phase diagram first. To understand, let's say this is my alpha, this is my beta. This is my liquid, alpha, beta, alpha plus beta, alpha plus L, liquid plus beta, and this is my liquid. Right. In eutectic solidification, you have minimum, like lower melting point when compared to melting points of their constants. Like pure A, pure B has a melting point of T1, let's say Tm1, Tm2, then eutectic will have, let's say Tm1, is greater than T 2M, it's greater than T eutectic melting point. That means the lower melting point, right? So that is what we've seen. Now let's just recall what we have did in phase diagrams, right? Let's suppose if you're trying to draw at this temperature and at this temperature. Why I'm trying to draw is because we are going to use the phase diagrams here again. So to make ourselves uh, more understandable, so I'm trying to draw the phase diagrams of these two different temperatures. Let this is TE, let this is as T1. Let me draw the phase diagram at first T1, but let's say let's draw TE. Okay, now yeah, at TE you have an alpha phase and you also have a beta phase, and so if we draw the liquid phase first. So you have a liquid phase here and you have beta phase. So if I draw a common tangent, then it will touch them all, right? So this is my alpha, this is my beta, then this will be my alpha plus liquid plus beta. So this is my G alpha, this is my G beta, this is my G alpha. Now it is at T equals to T eutectic temperature, right? Now what is at my at T equals to T1? Now this again. Let's draw one point at here also. So that let's say this is T2. Now let's draw T1. So this is my alpha, this will be my beta, and liquid is way above, right? So if I draw a common tangent, this is my alpha, beta, alpha, beta, alpha plus beta. Right. Now if I try to draw at another temperature, I'm just drawing to make ourselves familiar, to familiarize what we are going to do next. Okay. The next one is T2. I was writing it small form. At T equals to T2. What is of x and so there are 1, 2, 3, 4, 5 regions, right? We'll start with alpha. You still have a liquid. Then you have beta. This is our so these are my points. Let's draw it here. One region here, another region, and you'll have another region. So this is my G alpha, G beta, G liquid. So this is my alpha, this is liquid, alpha plus liquid, beta is beta plus liquid. Right. So these are one first region, the second region, third region, fourth region, and fifth region. Moving on to eutectic solidification. See, now in iron carbon diagram, iron iron carbide diagram, we have seen a place where at eutectic eutectoid point we have seen there is a formation of perlite. Right. So gamma will turn out to be what? Alpha iron plus Fe3C. Right. So this is our cementite. And you have right. So this is our regions, or we have a laminar structure. Right. We have alpha iron, then we have Fe3C. Again, you have alpha. Again, you have Fe3C. So this is what we have seen. Now, what happens in eutectic solidification? Eutectic solidification. Let's draw the diagram again. So I'm only concentrating on the eutectic point. Right. Let's say says yeah. So what is happening at this point? If I try to cool along this region, okay? Now, let's say there is a mold, and at the surface of the mold, there will be formation of, let's say, alpha, and because of the rejection, there is a formation of beta. Right? There is alpha, there is beta. When they try to grow, it will again reject at both sides. So there is again this formation of beta here. Again, there is a formation of beta here. Now again, there will be formation of alpha because of depletion of solid atoms here, and again it will reject. Again, there is a formation of beta. Again, they will grow. They not only reject this side, and to grow in this direction, because of this alpha rejection, whatever the alpha reject the atoms here, they will go because of the concentration gradient. They will come here. They will move here because of beta needs more amount of solid. So beta takes up solid atoms, and because of this concentration gradient, the this interface will move. Right. Now, how do we do that? Now, let's say we have infinite body. Right. So that's what we have been dealing with. So I mean the basic assumptions that we have been dealing with. So let's say this is my, let's do with homogeneous nucleation. Homogeneous nucleation, where I have a sphere of radius r, then my free energy, my total free energy will be minus the volumetric free energy, which is 4 by 3 by r cube times the delta Gv. Delta Gv means it is my G versus T. It's my solid, it's my liquid. That is the Tm. Now below Tm, and this is my liquid, and this is my solid, and this is the change in energy. It is GL minus GS. Plus, we have to create a new surface area. Right? We have to create a new surface. That will be equals to 4 pi r square gamma, the surface energy of this sphere. Right? Gamma. Let's say the solid is a liquid. SL. Here's the total energy of the. Sorry. Now, if it is equals to 0, let's say delta G at a R, radius R equals to 0. What does that mean? Right? That means let's do that. So we shall know what exactly is that mean times delta GB plus 4 pi R square gamma SL equals to 0. 4 gets cancelled. If it pi also will get removed, then we are remained with, let's take R square as a common. We have minus delta GB times R upon 3 plus gamma SL. Right. So now let's take out that r equals to 0. We know that r can be equals to 0. One thing is, if r equals to 0, this whole term will becomes 0 because there is no transformation, right? So there is no formation of any free energy or nothing coming out. So that thing we can take out that. We can take out that case. Now the second case is this one. If this is equals to 0, what does that mean? R equals to 3 gamma SL upon delta GB. Right? Now we have seen R equals to 2 gamma SL by delta G, which is our R star, the critical radius. Right, if you try to differentiate it, then you will arrive to this one. I hope we all know how we arrived to this because I have done it many times. Now, what is the difference between these two? The term 3 and the term 2. Now, if this equals to 0, then that means the nucleation stops. Or the delta, if the R is equals to this one, then whatever the energy that is provided by the volumetric free energy or the change in GL minus GS or the transformation from GL minus CS is completely used in the production of this area or the production of surface. Right? So that means after this, the nucleation will not go. That is what it means. Right? Because there is no extra energy to supply, right, to form the surface area. Now, again, coming on to the new, this one, these guys, let's say this is my, yeah, where are we? Yeah. Now, let's say the interlaminar spacing or between 2, 1 for the thickness of alpha plus beta will be equals to lambda. Okay? Now, we can have an ideal case where lambda equals to infinite. That means we are dealing with total volume. That means the delta G term has, the total term will have, or the two terms that it has, one is the volumetric free energy, the area part, the surface free energy. Right? Now, if this lambda equals to infinite, then that means this term will dominate. Right? No. So let's that means this term will totally dominate and this term will go away. That means we have lambda equals to infinite. That means we have so much amount of volume. That means so much amount of volume that we are neglecting this area. So that is what it means. No, that is the at most ideal case. Now let's not go into model case. Let's take lambda is some constant. Right, lambda has some constant value. Okay, C1. Now, if I write this, delta gt will be equals to minus delta g if lambda equals to infinite plus 2 gamma alpha beta times molar volume or the volume upon the thickness. Right, this thing we derived from Gibbs Thompson equation. Right, so if you do not know, please refer to previous sessions. I have derived this part again. Now, there is another question: why these lamellars have this curved surface? Right, why do they have this curved surface? Why cannot they have like parallel interfaces? Right, so why can't they have like this instead of this? Why cannot they have like this? Right, this is suppose this is alpha beta alpha. This is alpha beta alpha. Why cannot they have like this? Now, to understand that, we need to understand how the surface energies are being balanced. Right? Let's write this part. Okay. First, let's write the columnar one. This guy. Right. Now let's zoom on this surface. Then it will mostly look like this. Right. Now what about this is our interface. This is my liquid. This is my alpha. This is my beta. Right. Now this will have where's this part and read it again. And the surface energy, surface energy between this is gamma beta L. The surface energy between gamma alpha L. And this is the surface interaction between gamma alpha beta. And they make an angle theta with the normal. Let's assume they make an angle, each make an angle theta with normal, even though that is not the case, because let's assume that as because the alpha surface interaction with liquid is different when compared to beta. So it should be theta 1 and theta 2. But for simple cases, let's assume that. Okay. Then if we balance the vertical forces and horizontal forces, right? So first let's balance vertical forces. Vertical forces will have gamma alpha cos theta. Now again, why they do not have theta 1 theta 2? Right, as I've said before, if gamma alpha and gamma beta are different, then we will have theta and theta 2. Let's see what will happen. So let's say this is gamma alpha L cos theta plus gamma beta L, or the beta liquid interface, times again cos theta, that will be equals to the vertical one is gamma alpha beta. So gamma alpha beta will be equals to cosine times gamma alpha L plus gamma beta L. This is our one condition. Now what about the horizontal one? This is about vertical forces. What about the horizontal forces? Now horizontal forces we have gamma alpha L sine theta, that will be equals to gamma beta L sine theta. So that means gamma alpha L will be equals to gamma beta L. So this is our assumption initially, right? Now, if they do not have the same cosines or the same angles, wetting angles, then surface tension angles, then what will happen? Gamma alpha L sine theta 1 will be equals to gamma beta L sine theta 2. This is our horizontal one, and the vertical one will be alpha gamma alpha beta will be equals to gamma alpha L cosine theta 1 gamma beta L cosine theta. So see, we can see here, whatever the case is, the forces are balanced. But if we take a plane interface, right? This is my alpha, this is my beta, and this is my gamma alpha. This is my liquid, right? And this is gamma beta. This guy is gamma alpha beta. Now let's balance the horizontal forces, right? So if I try to balance the horizontal forces, the gamma alpha will be equals to gamma beta, okay? Which is not worrisome. We even got here. Now what about the horizontal forces? Who is going to balance this one? Right? So there is no balancing here. So that's why there is a non-equilibrium condition in planar interface. So that is the reason why this, if there is, for example, if for some unforeseen circumstances, there is a formation of planar interface, gamma alpha beta, gamma alpha L, gamma beta L, then because of this non-balancing force, this will drag this surface downwards, and because of that, they will slowly, first there will be planar, and because it will drag a bit. Again, after some time, again, more dragging will form. So finally, you will have this columnar region where these forces will be finally balanced. So that is why this is more equilibrium shape when compared to this stuff. Now, that is all about the equilibrium. Now let's draw how the lambda will change. Right? Now this is delta G of lambda, that is equals to minus delta G of lambda, lambda equals to infinite, plus 2 gamma alpha beta molar volume upon lambda. Again, for a lambda star, where the growth will, I mean, the interplanar spacing, or not interplanar spacing, the interlaminar spacing will diminish. It will not grow further. How do you define that? Easy, just like we have done before. Equate it to 0. You will have 2 gamma alpha beta times Vm times equilibrium temperature, effective temperature here, or change in enthalpy times delta T naught. This is the undercooling. Right, now what does that mean? If we increase the undercooling, the interlaminar spacing will decrease. Now if I decrease the undercooling, so now this is how we have arrived where delta G lambda equals to infinite. That means a very large one, then delta H, we have no surface term, right? The quantity. So this is what we substitute there. Then if this delta H delta T upon TE is equal to this term, the surface area term, 2 gamma Vm upon lambda. So that means
there is a max
there is a
that you
max
can allow
that you can
at a
allow
certain underscore.
at a certain underscore.
Or is the max
Or is the max
lambda
lambda
or the
or the inter
dendrite spacing
dendrite
that you
spacing
can allow,
that you can allow,
right? Or the thickness
right?
of
Or
alpha
the
and beta
thickness of
that you
alpha
can
and
allow
beta
at a
that you
certain
can allow at a
underscore.
second underscore level.
Now,
Now,
how does this
how does this
front course? As I've
front
said
course?
before,
As
let's
I've
say
said
this is my
before,
alpha
let's say
and
this is my
beta,
alpha
and
and beta,
alpha
and
rejects
alpha
the
rejects the
solid atoms,
solid atoms,
right? And this
right?
will be
And this
transformed,
will be
and this will
transformed. I
diffuse
mean, this
from
will
here
diffuse
to
from
here.
here
So
to
there is
here.
a
So there
difference
is a difference
in
in
concentration, and that is
concentration,
given by
and that is
delta
given
x.
by delta
And
x.
this,
And this,
so the
so
velocity
the
with which
velocity
it
with
grows,
which it
it depends
grows,
upon,
it depends upon,
right? So the velocity
right? So
with
the
which
velocity
it
with
grows,
which
it will
it
depend
grows, it
upon
will depend
the
upon
concentration
the
difference,
concentration difference,
delta
delta
x v,
x v,
right? Again,
right?
it
Again,
also it is inversely
it is
proportional to
inversely
1
proportional
by
to
lambda.
1 by
See, it's
lambda.
just
See, it's just
normal. So
normal.
let's suppose
So
this
let's
distance is
suppose
very
this
much
distance is
large.
very much large.
So
So
if
for if
distance is very large, then
distance is very
the
large,
atoms
then
have
the
to cover a
atoms
larger
have to cover a
distance. That
larger
means
distance. That means
to come
come
from
from
alpha
alpha
to
to
beta.
beta.
So
So
that's
that's
why
why
the
the
velocity
velocity
front
front
will
will
also
also
decrease.
decrease.
So this is our
So
that. Then
this is our
also
that.
the
Then
velocity
also
will be directly
velocity will
proportional
be
to
directly
diffusion alpha
proportional to
terms.
diffusion alpha terms.
Right, higher the diffusion,
Right, higher
higher
the
will be the
diffusion,
velocity.
higher will be the velocity front.
So after
So
combining these
after
three
combining these three
empirical relations,
empirical
we will get
relations, we will get
a constant
a
proportionality
constant
constant
proportionality
K1
constant
times
K1
D
times D
delta XV
delta xv
upon
upon
lambda.
lambda.
This is one
This is one
empirical relation.
empirical relation.
Now,
Now,
how do we arrive?
how do we arrive?
Now the next one
Now
is
the
how
next
do we
one
know
is
this
how
delta
do we know
XV?
this delta
So
xv?
how do
So
we
how
know
do we know
this delta XV?
this delta xv?
How do we know that?
How do we know
So
that? So
delta XV
delta xv
will be equals
will
to
be equals
what?
to what?
XV
xv
at liquid plus
at
alpha
liquid plus alpha
minus
minus
XV at
xv
liquid
at
beta
liquid
interface.
beta interface.
Right? Now how
Right?
do you know
Now
that?
how do you know that?
And also
And
at
also at lambda equals to lambda
that means the
star, that
maximum
means the
allowed
maximum allowed
distance between
between
or the thickness
or
of
the
alpha plus
thickness of
beta
alpha plus
for
beta,
which
for which our
our
delta
delta
g
g
equals
equals
to
to 0.
0.
That
That
means
means
the
the
delta
delta
x
x
equals
equals
to
to
0.
also 0.
Right?
Right?
Again,
Again,
taking that
taking that
in mind,
in mind,
so we can again
so we
write
can
this
again
empirical
write this
relation. So
empirical
delta x will be
relations.
equals to
So delta
delta x naught
x will be
when
equals to delta
when
x naught
lambda
when
equals to infinite.
when equals to infinite.
So that means you
So
can
that
get
means
an empirical
you can
relation
get a
like
empirical
this when
relation like this when
1 minus
1 minus
lambda star. So
lambda
you
star.
will have obviously you will
So
have
you will
lambda
have
here.
obviously you will
So
have
if
lambda
this
here.
tends to
So if this
infinite,
tends to
then this
infinite,
will be equals
then
to
this will be equals
delta
to
x equals to again
delta
delta x.
x equals to again delta
Right?
x.
Again we are at
Right?
the same
Again we are
equation.
to the same equation.
So
So
this is our
this is
first
our
relation.
first relation.
And
And
what do we know? Delta
what
x
do we
naught
know?
is
Delta x naught
proportional to,
is proportional to,
as I have said before,
as I have said
the
before,
delta x naught will be
the delta x
proportional
naught will
to
be proportional to
the delta t naught,
the delta t naught,
the undercooling.
the undercooling.
Right? Now,
Right? Now
upon
upon
equating all these
equating
terms,
all these terms,
let's
let's
say
say delta x naught equals to
K3
k3
delta
delta t naught.
Okay?
Okay?
Then
Then upon substituting here, delta x will be equals to k3 delta t naught upon 1 minus lambda by lambda star.
And this,
And this,
if I substitute
if I substitute
xv,
xv,
this term
this term
in
in
here,
here,
the velocity term,
the velocity will be equals to
K1
k1
d,
d.
what is the delta xv?
What is the delta xv?
K3
k3 delta t naught 1 minus lambda by lambda star upon lambda.
Right.
Right? Let me add one more slide. We write this equation. V equals to
now,
now parting
the
with the
constants
constants
K1 and K2,
k1 and k2, K1 and K3. Sorry. K1 and K3. And you will have D and also delta T naught. And I have 1 minus lambda star upon lambda upon another lambda. It's lambda star. Really no lambda, right? So yeah, this is our final relation. Right.
So maximum speed
So
can be
maximum speed
attained
can
when
be attained when
lambda equals to
lambda
2
equals
lambda
to
star.
2 lambda star. Oh, my bad. We wrote this equation wrong, right? This is lambda star upon lambda. This one is correct. Yeah. Lambda star, we'll have lambda star here. Again, we will have another lambda star. Will be my lambda. Right. When lambda equals to 2, 2 lambda star. And equals to 2 lambda star. Then this can be written as K2
or K for anything.
or K for anything
As we wish.
So V will be equals to K2 D delta T naught divided by 2 lambda star.
Right.
Right.
This is
my max velocity. V naught. Or if we take and we also know delta T naught will be proportional to delta T naught is proportional to 1 by lambda star.
This we have seen
there. Right. Now if I substitute here, so V naught times lambda star square equals to C.
So this is our
final relation. V naught. That means V naught is inversely proportional to 1 by lambda star square. Or you can write it as V naught is inversely proportional to, or V naught is directly proportional to delta T naught whole square. Right. V naught if undercooling increases, then V naught will be doubled. At square. 2 the square times of.
Right.
So this is all about the growth.
Now, finally coming to the phase transformation.
The phase transformation part.
Okay, we have seen.
There are different types of phase transformations.
What we have seen.
We have seen the solid to liquid type 1, which is solidification or melting, and from liquid to solid we have seen as solidification. So this is our solidification.
Right.
Now the next one is we have seen solid to solid transformation.
And from this
we have seen eutectoid reaction, you take
Tried reaction,
tried reaction,
peptide
peptide
transformation,
transformation,
where one solid
where one solid
will
will
give rise to
give rise to
two types of
two
solids,
types of
right?
solids, right?
Solid
That is
one,
solid one,
solid two,
solid
solid
two,
three.
yeah, solid three.
Now from this,
Now from this,
there is a term,
there is a
okay,
term,
which is called
okay, which is called
precipitation
precipitation
reaction.
reaction.
Precipitation reaction.
Precipitation reaction.
Now how does it
Now,
happen?
how does it happen?
Now these type of
Now, these
reactions are
type of reactions
extensively
are
used
extensively
for
used
the
for
precipitation
the
hardening.
precipitation hardening.
Precipitation
Precipitation
hardening.
hardening. Hardening.
Right. So these types
Right.
of
So these
are
types of
used
are
in the
used
precipitation
in the
hardening.
precipitation
So
hardening.
what
So
actually
what
happens is
actually happens is
let's start phase
let's start
diagram.
phase diagram.
Let's
Let's
say
say
you
you
have
have
a
a
big region here,
big
which
region
is a
here,
solid
which is
region.
a solid
Let's say
region. Let's
I
say
have
I
gamma
have
here,
gamma here,
I have alpha,
I have
and
alpha,
here I
and
have a
here
beta
I
region.
have a beta region.
Now,
Now,
what do you mean by
what
precipitate
do you mean by
formation?
precipitate
Means,
formation?
let's
Means,
say
let's say
I have a
I have
composition
a
of,
composition of,
let's say this is my
let's say this is
composition
my composition
X1, and I
X1,
have a
and I have
composition
a composition
this here,
this here
X2, right?
X2,
And I am
right, and I am
temperature
at
T1,
temperature T1,
right? For example,
right?
if
For
I have
example, if
a
I am
composition
a
X2, let's say
composition
this is
X2,
pure A,
let's say
this is pure
pure
B,
A, this is pure
and if
B,
I have
and if I have
a
an
metallic sample,
metallic
and if I
sample,
heat treat
and
it,
if I heat treat it,
and if I
and
homogenize
if
it
I
at
homogenize it
T1,
at
that means I'm
T1,
keeping
that
it
means
for
I'm keeping it
like more
for
than
like
40 or
more
50
than
hours
40 or 50 hours
to form
to
a single
form
phase,
a single phase,
right?
right?
Let's say we have
Let's say we
alpha
have
everywhere,
alpha everywhere,
okay?
okay?
To form a single phase
To form a single
alpha
phase
everywhere,
alpha,
to form a
everywhere
homogeneous
to form
solution
a
of alpha
homogeneous
phase.
solution of alpha
That
phase.
is that
That
is
is
what we're trying
that
to
is
do
what we try
homogenization.
to do
Now what I'm trying to do
Now
is
what I'm trying to do is
I try to cool it
I
down,
try to cool it down,
right? I'm at
right?
T1,
I'm at
set
T1,
composition
set
X2.
composition
Now what
X2.
I'm trying to do is
Now
I'm
what
trying
I'm
to
to do is
cool it
I'm trying to cool
below
it
T1,
below T1,
right? So let's
right?
say
So let's
I
say
came to
I came to
T3,
T3,
T2.
T2. Okay.
So still
So
there
still
is my
there is
alpha
my
grains,
alpha grains,
right? So
right?
alpha,
We have alpha, alpha, alpha.
T
When at
equals to
T
T2.
equals to
Now
T2.
again I
Now
cooled it
again
down.
I cooled it
So
down.
what happens is,
So what happens is,
and because of this,
and because of this,
now I
now
cooled it down
I
from
cooled it
T2
down
to
from
room
T2 to
temperature,
room temperature,
right?
right?
I cooled it down.
I cooled it down.
I quenched it. For
I
example,
quenched
if
it.
I try
For
to quench
example,
it,
if I try to quench it,
right?
right?
So again,
So again
I have
I have
alpha phases,
alpha phases,
but
but
there needs to there
there needs
so
there
at
so
room temperature
at room
the
temperature
equilibrium
the
diagram should be
equilibrium diagram
this
should
one.
be
That means
this one.
we
That
should
means
have
we
alpha
should have
plus
alpha
beta. I
plus
mean the
beta.
more amount
I
of
mean the
alpha and
more
less
amount
amount
of
of
alpha and less amount of
this fraction of
this
beta,
fraction of
right?
beta,
But
right?
we do not
But we
see
do
that
not
here.
see that
T
here.
equals to
T equals to
RT,
RT,
the room temperature.
the
We
room
do not
temperature.
see
We
that
do
here.
not see
Now
that
the
here.
reason is
Now the reason is
we have quenched it now,
we have quenched it down,
right? We totally quenched
right?
it.
We totally
Now
quenched it. Now
what we do is we try
what
to
we do
heat
is
it
we try to heat it
from room temperature
from
to,
room temperature
let's
to,
say,
let's say
2 point
2 point
T3.
T3.
Let's
Let's
say
say
I'm
I'm
heating
heating
the
the
sample
sample
to
to
point
point
T3.
T3. Now what happens?
Suppose this is my
Suppose
sample
this is my
and
sample
these
and these
are my grains.
are my grains.
Now after
Now
quenching,
after quenching,
it is at room
it is
temperature.
at room
It has
temperature.
alpha.
It has alpha.
Now what I'm
Now what happens? Now
this one is called
this
as
one is called as
super
super
saturated
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 solid
solid
solution,
solution.
right?
right? Why I'm calling supersaturated solid solution? Because it has exceeded its solubility limit, right? At room temperature, this is the amount of B atoms that the alpha can maintain. But because of the quenching, it is maintaining more than that. That is, it has exceeded saturation limit. That's why we call it as a supersaturation solid solution. Now, once we heat it, whatever the solute atoms that were there, they will try to come out and they will precipitate out. Just like in solutions, because of solubility product, once that is a solubility product, they will precipitate out. So, alpha, alpha, there will be precipitates forming all those regions. Why? Because supersaturation, right? It has reached the solubility limit, and these are beta phases. Right. So these are my beta phases. Beta phase. And why do we do this? And because the deformation is nothing but moment. Deformation mostly in most of the materials is nothing but moment of dislocation. Now, when these dislocations move, and if
you want to deform
a material, there should be a free movement of dislocation. If there is any obstacle, just like this precipitates, right? So these precipitates will come into picture, and they have different crystal structure also. So maybe if suppose if they are more hard when compared to this alpha matrix, then these dislocations cannot freely move beyond this precipitate. And because of this, there is an obstruction, or there is a stress field. Suppose, just like I have said before, when we have discussed in interfaces, the precipitates have their own crystal structure, right?
Let's say
if they have some different parameters when compared to
alpha phase,
then there will be strain.
Then there is
a strain factor that's been accommodated here.
Right, there
is also straining in atomic length. And around the dislocation, there is also a strain field distribution around this dislocation. And there is also the strain field around this lattice parameter. And because of these two strain fields coming into contact, most of the time the dislocation cannot strain more of this atomic. And that's why, because these precipitates will act as the obstacles for it. And these dislocations cannot freely move. That means we are restricting the motion of dislocation. That means we are increasing mechanical properties. Properties of our system. And this will continuously take into whole another course. So we are not going to discuss about it. So this is the basic understanding of these things. So yeah.
In next few
sessions we will discuss about the different types of phase transformation. So
that's all for this session.
Thank you.